Good morning.
Good morning.
What we've got here. Okay, today is all about practice problems. Answering your questions and doing practice problems. And let's see. There's a assignment up. Is it due tonight?
Yes, sir.
Yeah, it's due tonight.
Okay, and then there's another one due Monday. Did you know that?
On the 7th?
Yep.
Yeah,
This one's
okay.
a timed event.
That's the timed event. Yeah, so
Yes, sir.
that's what I didn't know. I didn't know since it doesn't become available to you, I don't know how much warning you get with stuff like that. So it does tell you to expect that. And the timed event means 24 hours. So again, it's meant to be, what I did is I took basically a test that would be an in-class test for 50 minutes and took a couple questions away from it. So in theory, you know, if you were doing it on pencil and paper, it would be less than 50 minutes. Sometimes technology makes it slower. So you should have plenty of time to do that. And I don't have very many of those throughout the semester. Thank you, Casey. Okay. All right, let me share my screen, and then I'm going to ask you guys for questions, and then from there, if there aren't any questions, I'm just going to start working through practice problems. Okay, this is me preparing for practice problems. Do you have questions about the material that we covered or about the practice problems?
Are you able to go a little bit more over regular expressions? Because I'm not fully understanding that, I guess.
Oh, okay, yeah, so let's look at these. So regular expressions, I'm sorry, let's go back to the definition real quick. The empty string is regular. Any single symbol in the alphabet is regular. Now let's stop there. The rule in terms of grammars was that you could create a grammar that has exactly one non-terminal on the left-hand side of every single rule. And on the right-hand side, you would never lose a terminal once you got it. And you can create at least one grammar where you build the string from left to right. So if we look at those first two, I'm going to say that the lambda is in there because I cleverly put these up so I can cut and paste. And that may be a there's my rule. I hate PowerPoint so much. Okay. There's my rule, right? Start string to lambda. So it's regular because I can create a grammar that matches the requirements of a regular grammar. One non-terminal on the left-hand side of every rule, and I create the string from left to right. I guess if the string has no length, I don't know what left and right means. And then I can also do that for every single alphabet in a language. I can create a grammar that does the same thing. So that's just getting you to the individual elements of the alphabet are regular. Once we have that, now we start to do recursive definitions to build new strings that are also regular. If U and V are already regular, then U concatenated with V is already regular. is also regular. And so the idea behind that is, we said that A was regular. Well, if I concatenate A with A, that is still regular. We said that A was regular, and we said if I have my sigma, if my alphabet is equal to AB, then I have A is regular and B is regular, which means that I can concatenate them like that. Well, now I have two strings which are already regular, so that means that I can concatenate them together, and I can be guaranteed that that's regular. Once we have the idea of concatenation one time, we can say, why not do that forever? And that's what the U star, the clean star, and the U superscripted plus sign is. The U star and the U superscripted plus sign. U star means 0 or more copies, and U plus means 1 or more copies. How does that work in the grammars? A star means it's equivalent to nothing, lambda. I'm going to go back to that way. Or A, or AA, or AA, and we can keep going. Right? That's what sigma star, that's what the clean star means. A plus, and I'm not, excuse me. Come on, move, move. Come on. There you go. Dog throwing up. A plus means A or AA or AAA. It's the same as the clean star, except lambda is not included. How does that work for groupings of things? If I were to say ABA, that whole quantity starred, I'm going to use plus, then it's ABA or ABA with another copy, ABA, or ABA with another copy, with another copy. That whole thing inside the parentheses gets copied over and over and over. And then the last is the OR operator. And the OR operator says, if I have U or V, then I can pick one. Now, if I do something simple like A or B, then I can pick an A or a B. And if I put the clean star on it, what it means is I can do that as many times as I want. So if I wanted to make a string of length 5, let's say I wanted to go through and use the clean star and make 5 copies of A or B, that's A or B, A or B, A or B, A or B. In other words, I could pick an A the first time, I could pick a B the second time, the third time, fourth time pick an A, fifth time pick an A. I can get basically all possible permutations of A's and B's of length 5. Now let's bring that to, let's bring that to the sample problems. L1 is just A star. So what are the strings of A star going to look like? If that's the language, in natural language, can you explain what that is? And can you give me some sample strings that are in that language? Just unmute yourself and shout it out.
Any number of A's.
Any number of A's, right. Does that any number include 0?
Yes.
Yes. So a string that would be in there is lambda and A and AA and AAA, right? So what would that grammar look like? Well, the easiest way to make any number of A's would look like this. Grammar would start with the start string. And I'm going to go to just non-terminal A. And then non-terminal A goes to terminal A, non-terminal A, or lambda. Now think about how that grammar works. If I wanted to derive strings, I start with the start symbol. I start with the start symbol. My initial string is always just the start symbol. And then let's call this rule. My touchpad's too sensitive. It thinks I'm changing the size all the time. And yes, I do cuss when I'm not on being recorded when that happens. That's rule number 1. This is rule number 2 and 3. Okay. So going from A to A, little a is rule number 2, and going to lambda is 3. So if I have to use rule number 1 first, and then if I wanted to make the string, you know, AAA, then I would use rule 2, rule 2, rule 2, and then finally rule 3. And what did rule 3 do? It replaced that capital A, the non-terminal A, with the empty string. That's why it just disappeared. Okay, looking at these languages, which ones gave you issues?
Wait, Grayfield, aren't
Pardon?
languages the way they're written the same thing as how you would write a regular expression?
Yeah, these are regular expressions.
Okay, that's what I was wondering because I didn't know if they were different.
No,
Okay.
these are all given as regular expressions.
Also, I have a question about grammars. If
Yes.
for like on the homework when I was trying to see if I made a correct grammar, it's you have a correct one when you can't produce any strings that violate the rules, right?
You have to do 2 things. Create all the strings that match the rules, and you cannot create strings that violate the rules. And yes, that can be difficult to figure out sometimes.
Yeah, because I realized the first one I did, I was like, oh, wait a minute. No, that's not right. And then
Yeah.
So I just wanted to make sure I had that right.
Right. It happens all the time. Right. And the more bizarre the irregular expression, the harder it is to convince yourself that you got it right. Like language 1 there, you know, I'm starting with the easier ones and moving up, right? So language 1 there, which is the A star, it's pretty easy to figure out if you violated the rule. If you have a rule that creates a B, a terminal B, that's no good. Okay.
Gotcha. Thank you.
Oh, look at that. My 10 didn't get subscripted properly. All right, let's do language 2 then, since I don't hear any volunteers yet. Language 2 is ABA star. This thing assumes you always want to subscript. And it's awfully hard to get rid of that. Okay, so that's ABA star. So our grammar I've been using capital A is a mnemonic when I want to create little A's. And there's nothing magical about it. I'm going to use, I don't know, D, just for the heck of it. It doesn't matter what you use. And then I'm going to do D goes to ABAD. And that's it. Whenever you have a clean star like this, all you have to do is take whatever's being repeated, put it in your grammar, the terminals in the grammar, followed by whatever non-terminal that rule is attached to on the left-hand side. So think about strings that are in the language. Lambda's in the language. ABA is in the language. ABA is in the language. ABA is in the language, and so on and so on. Can we create the first string, lambda? Well, we start with the start symbol. We use rule 1 to get the D, and then we get lambda. We start with the start symbol. We use rule 1 to get the D, and then we use rule 3 to get the lambda. Can we create ABA? Yep, we start with the start symbol. We use rule 1 to get the D. We go ABAD using rule 2, and then ABA and get rid of the D using rule 3. In order to get this string, ABA, ABA, by the way, this starts to get boring quick, right? Because we're just going to do the same thing over and over. Use rule 2, and then using rule 3. Do you see how this format, non-terminal D goes to ABA non-terminal D, allows you just to keep creating copies, as many copies as you want of the ABA. This is a pretty standard form. I'm going to go to the next language. If you have issues, let me know. Now this one with BB is going to be exactly the same. It's just instead of ABA, I put BB in there. So let's go to this one. The language is BB star, AA, BB star. Can you do problem G? The L7? Yeah, we can do that. We can do that. Let's see. So L7 is A star, B star, or B star, A star. By the way, if I did this, A star, B star, let me start with that. If I had A star, B star, that's all the strings that start with A's. All the A's have to appear before all the B's is what that is. But you don't have to have any A's and you don't have to have any B's. So one way to do that is to do this. That's one grammar. I missed the I missed the chat. Now, if I wanted to do the opposite, where it was B star, A star, it would look really similar. It would look like rule 1, S goes to BA. That make sense? Now to make the full language, I say, okay, I'm either going to make the strings that are all A's are before all B's, or I'm going to make the strings that are all B's before all A's. Both of those are in the language. So let me do a cheap trick. I'm going to call this S prime. I'm going to call this S double prime. And I'm going to have a rule, my rule 0, S, whoops, S goes to S prime or S double prime. Does that make sense? So my grammar, this is actually the first rule of the grammar right here. And now
Hey, Garfield, so you basically created 2 separate grammars and then just said, go back to start and pick one, pretty much, either
Yep.
or.
because that's what the language tells me to do, right?
But are those 2 grammars that you created not the same? So, and that's why you're able to use the S prime and S double prime?
What do you
They're
mean
just
by the same? Yeah.
because, for example, with the rules 2 and 3,
Yeah.
and the rules where they're at 9 and 10,
Yeah.
the A both goes to low A, upper A.
Yeah.
Okay, and so that's why with the rule 0 we can do the S prime double prime.
Yes. Because what,
Okay, cool.
what rules 1 through 5 will create all strings where the A's come before the B's, but you don't have to have any A's and you don't have to have any B's. So rules 1 through 5 create these strings. And rules 6 through 10 create these strings. See that you're right. Rules 2 and 3 are the same as 9 and 10, and 4 and 5 are the same as 7 and 8. And the only difference is rule 1 sequences with them with the A's first, and then the B's, and rule 6 sequences them with the B's first instead of the A's.
Okay, yeah, that makes sense.
Right. Now, if I wanted to clean it up a little bit, I would do this, because I don't need S prime and S double prime, and I would say, okay, I only need those rules that we had initially, and then you can either put all the A's before the B's, or you can put all the B's before the A's. Right? All I did was I kind of collapsed those rules. Is that one step too far?
Makes sense.
Okay. To one of you, but there's 20 or so on the call.
No, yeah, it makes more sense that way.
Yeah, I understand it better now.
By the way, here's a cheap thing. Remember, we're making the claim. We're making the claim that if, if U and V are already regular, then U or V is regular. And we just proved it, if you think about it. if I have some language one, let's go, I can't use subscripts very well. So let me use language. Oh, see, once you get a subscript in Notepad or PowerPoint, it refuses to go away. So let's say you have two languages, L prime and L double prime. That means you must have two grammars, grammar prime and grammar double prime. And grammar prime starts with S prime, and grammar double prime starts with S double prime. And so if I made a new rule that said S goes to S prime or S double prime, haven't I proven? As long as I have a regular grammar for L prime, it must be regular. If I have a regular grammar for L double prime, it must be regular. And if I just say in front of this, hey, pick one of these start symbols. Start symbol S prime is going to give you L prime, and start symbol S double prime is going to give you L double prime. So that's an OR operator there, right? Pick one or the other. So we've just proven that if L prime is regular and LG prime is regular, then their OR operation is also regular. That's the kind of stuff that these formalisms allow, is proving things about properties of languages. And we took advantage of that here in a specific case, but it holds whether you've specified what those languages are or not. Things can get pretty theoretical pretty quickly if we choose to, which means I noticed things got pretty quiet pretty quickly. This one's the same trick, right? It's just a little easier, right? L7, the individual pieces were A star, B star. L6 is a little bit easier because it's A star or B star. Let me jump backwards to L4. Who has a grammar for L4? Anybody? L4 was BB star, AA, BB star. So what do the strings look like in L4? Is the empty string in L4? Is lambda in there?
No.
No. The smallest string is
AA.
AA, right. So the smallest string is AA. Then you can have as many pairs of B's ahead of AA as you want. So BB, AA, BB, BB, whoops, AA. Right. Can I have more than one pairs of AA?
No. No.
I can have things after though, right?
Yeah. Any amount of BBs after and before.
And on, and I can do any combination of that kind of thing. So if I'm going to build my grammar, and usually I, again, start thinking about what the smallest string is. I'm going to park that lambda down there so I don't lose it. What the smallest string is going to look like is AA. So I'm going to make a rule that goes right to AA. And then I have to be able to put BBs in front of it and BBs after it. So I'm going to put non-terminals in the front and back like that. And then rule 2 and 3 is going to look like need that lambda back. There it is. By the way, that's wrong. Why is it wrong?
because you have a
Two B's, right, Casey, good. Matthew, I finally saw your old message from, and yes, that's correct. All right, so I need two B's. They have to show up in pairs. The terminals have to show up in pairs. So that's right. That grammar works. We can create all the strings that we just talked about on the left-hand side with that grammar. Now, is that grammar regular? No. Correct. It is not regular. And why is it not regular? Because we're not creating strings from left to right. We've created them in the middle. I'm not sure what you're asking, Matthew. It's BB star, and so this lambda here gives us the star property, the zero, the option to have zero B's. For example, if I want to do string AA, that's the smallest string, right? I would go from S to B, AA, B, and then I could get rid of the first B using the rule 3, and then I could get rid of the second B using rule 3 again. But notice we did not create the string from front to back because we can create at either end. What type would this language be? That's a good question. Well, let's see. Is this a regular expression for L4? Is that a regular expression?
Yes.
Yes. So, yeah, Matthew, that's right. We needed both the B's in there. Yeah. So, yeah, that's a regular expression. So the fact that we can write this with a regular expression is a pretty strong indication that it's a regular language. Now, this particular grammar I wrote is not regular because it doesn't create the strings from left to right or from right to left. All we have to do, though, to prove that a language is regular is find just one grammar that you can do that with, that you can just find one grammar where you can go from right to left or left to right. And it's pretty easy to do that. What we can do is this. I'm going to go from, I'm just going to get rid of these. I'm going to use P, Q, and R. Shoot, I lost my lambda. Now, is that grammar regular?
Yes.
Builds the string from left to right, and the smallest possible string is AA. It meets our requirements for the language. So we have, as long as you can produce one grammar that's regular, then you know the language is regular. So we have different, we'll find out a couple of different ways to prove that languages are regular. That doesn't mean you have to have all the grammars. Remember, we can create an infinite number of grammars, most of which are useless, and many of which are going to be, the vast majority could be will be non-regular. That doesn't mean the language is. It just means that you haven't matched the grammar to the language yet. You know, sometimes it's more convenient. You can write a shorter grammar, right? This grammar is a little bit longer than the one we had before. So sometimes you can write a shorter grammar where the grammar itself is not regular, even though the language is. Let's see. This is all possible, all strings that end in BBB, and you have to have at least one A or at least one B before that. These are strings that start and end with A. Let's do L9. L9 is going to be the same trick. L9 is Was that a star or was that a plus sign? Star. It's going to be the same trick. This is actually going to be easier to write a non-regular grammar for. And the reason is I have to have the A and the terminal A and the terminal A at the beginning and end of the string. So why not just put it in there to begin with? I'm not going to put them on the same line. Then I can get a AT or BT or lambda. Did I get that right, by the way?
Yeah.
Yeah. Now, is that grammar regular? No, because I am growing the string in the middle, right? I put the endpoints on, I put the bookends on, and now I'm growing the middle. But the language itself is regular. If you wanted to create a regular grammar for it, then you would do that and that. Right. Instead of ending with a lambda, I have to have that A. Now, how do you know how to do this stuff? You know, that's why I gave you quite a few examples. And make your own up, right? I opened up a discussion session where you can make your own languages and see if people can create grammars for them or even define the language sets.
Garfield, I have a question on the one you just created. So
Yeah.
wouldn't lambda have to be an option because of the star, or am I understanding this wrong?
That's a good question. I like that question. So you're saying the smallest string in this language is AA, correct?
Yes.
And your question is, can we create that string? In other words, can we have 0 A or B options in the middle?
Mm-hmm.
So if we start with S and we use rule 1, we're going to go to AT. And if I use rule 2, 3, 4, the T goes to an A.
Okay.
Right? And these are exactly the right questions to ask. You know, you build the grammar, you start playing around with the strings and convince yourself, number 1, can you build all the strings you're supposed to? And number 2, are you not allowing strings that should not be in there?
Yeah, thank you.
Mm-hmm. Let me skip down. This will be our last one because I'm down here at the bottom, these properly nested parentheses. So now my alphabet is the left and right parentheses. And we do left and right parentheses. Has anyone created the grammar for that yet, by the way? Don't all jump in at once. It's pretty straightforward. Again, when you see these tricks and you see them a couple times, let me think, is the empty string in there? No empty string. So we have to have at least one pair of parentheses. So since I have to have at least one pair of parentheses, I'm going to put those right in at the top. And then I'll use P for parentheses. Rule 2 would just create more pairs. And rule 3 is going to be my lambda. So the trick is I never create a single parentheses because the rule is they have to be properly nested, so why not create them nested? Now the language, can I create that string? I just use rule 1 and then I use rule 3, right? This is rule 2, 3. So yeah, I can create that string. Can I create that string? I start with S. I go to that using rule 1. I use rule 2 to get that. I use rule 3 to get that. So hopefully you can see using rules 1, 2, and 3, I can create as many nested pairs as I want. That's not quite the language though, because this is also in the language, right? Whoops. So how would I get away with that? I add this rule. I can make copies of non-terminal P, and then in order to get rid of non-terminal P, I have to either keep creating nested, properly closed off parentheses, or nothing. So now I can get this string by going from S to by the way, you're only allowed to do one at a time. It's really annoying. So I can get there. Is that string in the language? We'd have to check the definition, right? I think it's that's properly nested, isn't it? I mean, from the just our common sense definition of what properly nested looks like, isn't that properly nested? I'm going to say yes. Can this grammar create that string?
No.
So let's fix it. Now can it create that string?
Yes.
I don't think I did it right yet, though. I think I have to do, because now I haven't created that string, right? I don't think my grammar will create that string. No, it will. Because once I get, we can do that. Which means I can actually do that. Yeah, it takes a while to convince yourself what's going on. I can actually do that. Now, one question before we close out. Is this a regular grammar?
No, you put it in the middle.
Right, we're not, it's not regular because we're not building from left to right, and we're not building from right to left. We're building in the middle. So it's the grammar is not regular. Do you think we could find a regular grammar for this? Not an easy question, by the way. By the way, I missed the comment. These comments disappear on my screen if I don't grab them quick enough. So that's, if I'm not responding to you in chat, that's why. There we go. Probably not. And there's a clue. I did not give you a regular expression for this language, right? If I didn't give you a regular expression for the language, it's probably not regular. And it turns out it's not. This is not a regular language. We'll find out why. In terms of grammars, it's kind of hard to explain. In terms of models of computation, which we'll discuss next week, it'll be much more clear. But the bottom line is this. your grammar has no memory. And if you're doing properly nested parentheses and you put 5 of them in there that need to be closed out, how do you know, how do you coerce the grammar to use the rule that creates those 5 times? And the answer is you don't have a mechanism to do that. So since we have to be able to, in a regular expression, we have to be able to create the strings from left to right or right to left. And so if I'm creating them from left to right and I'm merely creating left parens or open parens, but not worrying about the closed parens, I have no mechanism to ensure that all those open parentheses got closed at the end of the string. That's why we have to create them in pairs. And so if we're creating them in pairs, we're building the string in the middle with this nesting problem. So there is no mechanism that allows us to go from left to right or right to left. And this is one of the canonical non-regular languages. This is a context-free language. It's context-free because there's exactly one non-terminal on the left-hand side of every rule. We're building strings in the middle. And once we have terminals, they don't ever disappear. The other canonical language, which looks regular, but it's not technically regular, the other one is this, A to the N, B to the N, where these are superscripted. Oops, where the N's are superscripted. Let's do it programming-wise. A to the N, B to the N. And it's for the same reason. Here, I'm not just saying that I have A's and B's. I have the number of A's has to match the number of B's, and there's no mechanism once we start going from left to right, and here I am making all my A's, da, 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 and then I transition to where I'm going to start making B's. I have no mechanism in the grammar to say, hey, I created 462 A's at the beginning of the string, therefore I have to have 462 B's. The grammars don't have that mechanism. So we have to create these in a non-regular way. It's going to be context-free. And when we do models of computation next week, which is the finite state machines is what we'll start with, those match up to the regular languages, and we'll have a model of computation argument against this kind of a language being regular also. Okay. I'll be here Friday, but again, it's truly going to be student questions. I'm not almost certainly not going to talk if I can help myself. It's hard for professors not to talk, right? So by all means, let's treat Friday. All the lectures are optional, but there will be no new material on Friday. It's basically going to be an office hours kind of situation on Friday. You are welcome to be here. I will be here for the 50 minutes, and because it's more of an office hour situation, I don't plan on posting that lecture to YouTube. I think I also still owe you Monday's lecture on YouTube. Okay, quick questions before we go? All right, everybody. Have a great day.
Two.
Thank you.
Thank